Hi and welcome back to Down the Shed with me, Jason. So today we're not doing an experiment. We're literally going to be just reading a section of the electronic playground manual, which is an introduction to capacitors. So capacitors are electrical components that can store electrical pressure, brackets voltage, for periods of time. When a capacitor has a difference in voltage, electrical pressure across it, it is said to be charged. A capacitor is charged by having a one-way current flow through it for a short period of time. It can be discharged by letting a current flow in the opposite direction out of the capacitor. In the water pipe analogy, you may think of the capacitor as a water pipe that has a strong rubber diaphragm sealing off each side of the pipe, as shown here. If the pipe had a plunger on one end or a pump elsewhere in the piping circuit as previously shown, and the plunger was pushed towards the diaphragm, the water in the pipe would force the rubber to stretch out until the force of the rubber pushing back on the water was equal to the force of the plunger. You could say the pipe is charged and ready to push the plunger back. In fact, if the plunger is released, it will move back to its original position. The pipe will then be discharged with no pressure on the diaphragm. Capacitors act the same as the pipe just described. When a voltage, electrical pressure, is placed on one side with respect to the other, electrical charge piles up on one side of the capacitor, on the capacitor plates, until the voltage pushing back equals the voltage applied. The capacitor is then charged to that voltage. If the charging voltage was then decreased, the capacitor would discharge. If both sides of the capacitor were connected together with a wire, then the capacitor would rapidly discharge and the voltage across it would become zero, no charge. So basically, if you want to discharge a capacitor, you just bridge the wires with a metal object, but not holding the metal object. So let's say a plastic handled screwdriver or something. What would happen if the plunger in the drawing we just saw was wiggled in and out many times each second? The water in the pipe would be pushed by the diaphragm and then sucked back by the diaphragm. Since the movement of the water current is back and forth, alternating, it is called an alternating current, or AC. So basically your mains voltage is alternating, your battery is direct current, or DC. The capacitor will therefore pass an alternating current with little resistance. When the push on the plunger was only towards the diaphragm, the water on the other side of the diaphragm moved just enough to charge the pipe, a transient or temporary current. Just as the pipe blocked a direct push, a capacitor blocks a direct current, DC. Current from a battery is an example of direct current. An example of alternating current is the 60 cycle, 60 wiggles per second current from the electrical outlets in the walls of your house. That's possibly 50 in the United Kingdom. I think America uses 60. I'm prepared to stand corrected in the comments below. Construction of capacitors. If the rubber diaphragm is made very soft, it will stretch out and hold a lot of water, but will break easily. Large capacitor but low working voltage. If the rubber is made very stiff, it will not stretch far, but will be able to withstand the higher pressure, low capacitance but high working voltage. By making the pipe larger and keeping the rubber stiff, we can achieve a device that holds a lot of water and withstands high pressure, high capacitance, high working voltage, large size. So the pipe size is determined by its capacity to hold water and the amount of pressure it can handle. These types of water pipes are shown here. Similarly, capacitors are described by their capacity for holding electric charge, called their capacitance, and their ability to withstand electric pressure and voltage without damage. Although there are many different types of capacitors made using many different materials, their basic construction is the same. The wires, or leads, connect to two or more metal plates that are separated by high resistance materials called dielectrics. So that's the construction of a capacitor. The dielectric is the material that holds the electric charge pressure, just like the rubber diaphragm holds the water pressure. Some dielectrics may be thought of as stiff rubber and some as soft rubber. The capacitance and working voltage of the capacitor is controlled by varying the number and size of metal dielectric layers, the thickness of the dielectric layers, and the type of dielectric material used. Capacitance is expressed in farads. F, named after Michael Faraday, whose work in electromagnetic induction led to the development of today's electric motors and generators. Or more commonly, in microfarads, UF, millionths of a farad, picofarads, PF, millionths of a microfarad. Almost all capacitors used in electronics vary from 1 PF to 1000 UF. Your electronic playground includes 2 electrolytic, 110 UF and 100 UF, and 2 disc, 0.0047 UF and 0.047 UF capacitors. Mylar capacitors may have been substituted for the disc ones. Their construction and performance is similar. Electrolytic capacitors, usually referred to as lytics, are high capacitance and are used mostly in power supply or low frequency circuits. Their capacitance and voltage are usually clearly marked on them. Note that these parts have a minus and positive polarity. It is absolutely imperative when making circuits you get these right, and I didn't have one here to hand, I thought I had. Capacitance and voltage are usually clearly marked on capacitors. Note that these parts have a plus and minus polarity or orientation markings. The lead marked plus should always be connected to a higher voltage than the minus lead. All of your wiring checklists account for this. Disc capacitors are low capacitance and are used mostly in radio or high frequency applications. They don't have voltage or polarity markings. They can be hooked up either way. Capacitors have symbols as follows. So basically, as we've seen in a lot of circuits, your electrolytic or the tubular style capacitors will have a grey band on one side, and you've always heard me say when using capacitors, polarity, polarity, polarity. So the grey side is always negative. This should be matched to a short leg or lead, and the positive side will always have a long leg or lead. So even if you can't see the capacitor markings, the short leg is always negative, long is always positive. Disc capacitors, there is no polarity. You can put them in any way you want, it doesn't matter. So that is a little introduction to capacitors. So from now on, most of our circuits will be involving capacitors. Experiment number 7 is called slow light bulb, but that will not be the next video. The next video, just for those of you who watch all the way through, will be this little wooden Spitfire kit that I've just got from the local charity shop for £1.25, originally sold by English Heritage for £7. So that'll be a bit of fun. Thanks for watching the video, like the channel, subscribe to the channel, and I'll see you in the next video from down the shed.